Okay, hey. So this is part two of reverse engineering the keylogger. And the reason I'm doing a part two is because in the last one I just looked at the disassembled code, which is really helpful, and you always want to look at the disassembled code. But now I'm gonna show just shortly what the actual um what the actual assembly code looks like, and I'm gonna run through it. So you're gonna open IDA. If you don't know what IDA is, Google it, download it, and you're gonna click New, and you're gonna go into your source repos, Keylogger 1, x64 release, and exe. If you did the project I showed earlier, if you didn't, it's fine. I'm just gonna open it. I'm gonna click No here. Okay. So I already did all this again, so I'm just gonna run through it super quickly. So the keylogger file, if you remember from the last video, the disassembled code, I'm gonna run through how the actual assembly code looks like right here, instead of just the disassembled. So this is the actual disassembled code, but I'm not gonna do that right now. So I'm just gonna run through this super quickly, and again, this video is very advanced, but I will get into an introduction on reverse engineering. I'll get into like these general purpose registers, what call means, test, jump if zero, move, lead. Like I'll get into what all of that means. But right now I'll just get into this. So this is our keylogger function. Because I just showed the disassembled code, and you can kind of tell from the get async key state function. So this is pretty simple. Just looking at this, you should be able to break it down, but if you can't, it's okay. So we're moving 10H into ECX, right? Now, if you highlight ECX, you'll actually see all the other instances it's in. ECI. ECI is typically used for it's the source index, so that's usually used in like string operations most of the time. So we're moving, and actually if I highlight this too, you get to see all the other instances, which there's nothing here. So yeah, we're just moving ECX into ESI. Then we're moving 10H into ECX. Now if it's your first time ever reading this decompiled code, you'll go into Mozilla Firefox maybe, and you'll search up 10H in decimal. That's not a good. So go to a hexadecimal to decimal converter and type 10H, and that is 16. And it's getting async key state of the ECX, which ECX is 10H right now, which is 16 in decimal. And if we go to virtual key codes, because we know the get async key state is used to get key codes, if we look for 10H, so that in hexadecimal 10H, which is actually, I shouldn't have done that, but so I messed up right there. But so 10H, get async key state of 10H, it is the shift key, and you can see this is getting the shift key, and then it's testing AX, and this basically just checks and then sets the 0 flag right here, jump if 0. Now the get async key state, if you did not watch any of the other videos, the get async key state, it the return value, it actually returns 0 if the current desktop is not active, or the foreground thread belongs to another process, and blah blah blah. In other words, the key is not being pressed. So the get async key state function will actually return 1 if it is pressed. So when it tests AX and it says jump if 0, it's saying jump if 0. That means the 0 flag is 0 because it's not pressed. Because get async key state returns 1 if it is pressed. So if it isn't pressed, it moves down to here, our next instruction, and I'll get to that in a second. But if it's not jump if 0, So if it is 1, if getAsync key state returns 1, that means the key is pressed. We're gonna move the value of we're gonna move the memory address, because Lee actually moves the memory address of the source to the destination. So we're moving the memory address of A shift into RDX, and you can tell that is the string shift as it's shown here. Moving that into RDX, then we're jumping into this memory address, and that memory address is right here. As you can see, it's highlighted, and it is std outing. It is std outing RDX, or it's just it's std outing shift, and you're able to tell that from here. So let's say it's not pressed. Let's say it's 0. So jump if 0 to A, and that is right here. As you can see, it's highlighted. It goes here to our next instruction, which moves 0DH into ECX. Now, 0DH in decimal is actually 13, right? And if we try to, I believe actually it should just say DH right here. So you don't have to actually convert it. That is my fault. I apologize. So I think if we look for DH, or 0DH. Oh, okay. The H doesn't actually. Okay, so just 0D. Yeah, sorry. So just focus on uh, these first two integers. So 0D, it is the return key, enter. So jump if 0, if it's not pressed, it goes here, and we'll ignore that for now. Green, if you're not familiar with IDA, green just means that is true, that condition is met, and red means that condition is not met. So if the 0 flag, if it's 0, oh sorry, if it gets set to 1, because getAsync key state returns 1, and it's not 0, it goes here, and it says enter. We move the memory address of A enter into RDX, which is the string enter, and we are going here. And this is what's called an unconditional jump right here. This blue line, it means it's unconditional. So no matter what, the control flow will go this way. So it goes here, and it just outs enter, as you can tell. And again, this this right here. Actually, I have no idea why it's doing this, but yeah, it's just outing the enter string, as you can tell right here. RDX, yeah. So now let's say jump if 0. So let's say enter is not pressed. Then we're gonna go down here to our next instruction right here, and it's moving the integer 0 in 30h. Now 30h, the virtual key code 30 is 0, right? So it's moving 0 into EBX, and here it's moving EBX into ECX. So, and then it's calling getAsync key state. Same thing here. If it is pressed, so if it's not 0, we just out that integer, as you can tell right here. Because of, and if you can't tell here, it's just because I'm looking at this. We're just std outing right here. So yeah, and then yeah. So if it is 0, it's gonna go down. So 0 is not pressed. The integer 0 is not pressed. We're gonna go down, and we're gonna increment EBX. And if you remember, EBX is the value 0. So we're incrementing it by 1. So 30 by 1 is gonna be 31. So this is gonna be 31. It's gonna compare it with 9. So EBX, and EBX is used for our count. BX itself, BX. If you search up BX assembly, you'll see it's used for no. Let me search up EBX maybe. It's your I'm not sure. Oh, I'm sorry. ECX, ECS, ECX. So search up CX. It is the count register, and that is usually used for loop counts and iterative operations. And again, I'll really get into detail about this in the next videos. But yeah, so and if we have a for loop, say for int I equals 0x30, I will be our ECX, and that's just our loop counter. Because if you know in a for loop, for example, I, that is the counter. So if we're saying, let me open a notepad, not this one. So let me open that notepad. If we have int main, that's just function, and we're saying for int I equals 0, I less than or equals 30, I plus plus. And as you can see, I is our counter right here. So it's comparing, so it's moving EBX into ECX, which is 0, and down here, actually, it's not doing that. So it's getting EBX, and it's comparing 9 with it's comparing 9 with the current EBX value. So when this gets incremented, it becomes 1, and it compares 9 um, to 1. And it says jump if less than. JLE in assembly means jump if less than. And if it is less than, so obviously 1 in this case is less than 9, it's going to go back up. And you can tell this is a loop because the green line, it goes like this. And then it tries to get async key state of 1. And then it increments again, again, and again, and again. And that completes. So that doesn't happen. From 1 to 9, nothing is pressed. We go down to here. We're seeing we're moving the 41H value, which is A, into EBX, and 41, if we look 41, that is A. We're moving A into EBX. We're moving this memory address into RDI, not super important. And unconditional jump, we go right here, and we're saying, and we're moving the value of EBX into ECX, and that is A. That's moving to ECX. This just you can ignore. It's not super important. And we're calling get async key state. We're testing to see if A is pressed. Jump if 0, if it's not pressed. And if A is pressed, we're outing it right here. Now, wait. Test AXX, RX. Yeah, so we're outing it right there. Now, if it is 0, A is not pressed, moving down to this loop again. You can tell this is a loop. And we're moving, we're incrementing EBX, which is A, and we're incrementing RDI, not super important. But when we increment EBX, what happens if we increment A? You're probably wondering. If we increment A, we get a 42, which is the B key. So now B key, we're comparing Z to B. 5AH is Z. You can see right here. 5A. I keep forgetting. 5A is the Z key. So we're comparing Z. Well, in this case, we're comparing B to Z, and we're saying jump if less than. And obviously, B is less than OX5A because B is OX42. That is lower in decimal. And if it is less than, we go back. We try to get B. And then we just, if that's not the case, we get C. We increment to D. You get the point until we get to Z. And if that condition isn't met either, we go here, and we are just calling the sleep function. We're moving ESI into XCE and DW milliseconds. I believe it should be up here. DW, yeah. So you can tell this function takes an argument DW milliseconds, and we are passing in sleep, or moving ESI to ECX. And if you remember, I said ESI is used for data transfers. So we're moving source index to ECX, and then we're calling sleep with the value of ECX, and then the unconditional jump, we are going all the way back up right here. So it's a while loop. And again, unconditional jump. And yeah, so now I'm gonna go to the main function and I'm gonna show this one. I'm not gonna cover the process info one. Uh, I might, but I just want to cover the main function first. So as you can see, this is a main function. We're taking into argc, into argv, construct argv. So you can tell this is a function that takes arguments. In this case, command line arguments, which doesn't matter. So, well, it does matter, but you know what I mean. So we're obviously getting ready for our we're setting up the stack frame right here. And I'll explain all of this if it's confusing. It's not a problem. So all this stuff here, and we get to ECX. What is ECX? R14D. And R14, I don't believe that is here. Yeah. So, but we know like ECX is usually used for input and output, and you can search these up. So like ECX assembly. Should probably just search up CX count register. Oh, okay. So I'm wrong on that. But we can tell it's taking. We can tell this is the command line argument because it's comparing it by 2, and it's just it stands out. Also, what's it called? We know this takes arguments, and ECX is a general purpose register used for storing data. In this case, so we're comparing ECX, which I think is argc by 2, and we're saying jump if less than. We're going down here. But if you look here, there's also 2 more arrows pointing here. And if we go up, one other arrow that points here is this middle one right here. And this middle one says we are moving the memory address of a help, which is the string dash dash help, into RDX. And if you want to see more instances of RDX, just go ahead and highlight it. And RDX, you'll get some more information on it. And wait, yeah, wait, yeah. So you'll get some more information on that, and I can tell that's the input, and it's calling memory compare. So if you remember get async key state, I said it returns 1 if it's true. Now memory compare, it's actually the opposite. When it's testing EAX, and it's jumping 0, memory compare actually returns 0 if it is true. So in this case, when it's testing EAX and EAX, if the command line argument RDX and dash dash help are actually equal, then it's gonna return 0. So jump if 0 in this case means they are equal. So you see how it can differ depending on the situation, and that goes down here. And there's another arrow that goes here, and that is this one. And if our command line argument is equal to dash h, we are memory comparing it, and if it is 0, we go here. So we know dash help go here, and if there's less than 2 command line arguments, we also go here. And an unconditional jump here. Oh, it goes here. Sorry, let's focus on this for a second. And then we're moving 1 into SIL. Really not sure what that's for, but we'll just keep that there for now. And then unconditional jump here, 2 to BL, not sure what that is either. Then we're jump if zeroing here. And if we don't jump 0, you see it kind of goes here. Invalid parameter info return. So nothing really important, no return. So let's just assume we go here. We go here and we're testing. Oh, and if you know what this is, please feel free to comment. But anyways, we're going down here. We're moving 1 into BL. And again, same thing here. If that's not the case, it's just invalid parameter, no info, no return, nothing important. So let's just assume we go down again, and we go here. and we're testing SIL to SIL, and we're saying jump if 0 here. But if you remember, SIL actually got set to 0 right here. So if dash h or dash dash help or less than 2 command line arguments are stated, then if dash h and dash dash help are our first command line argument, I'm assuming SIL is set to 1. When we're testing SIL here and we're saying jump if 0, then it's not 0 because SIL just got set to 1. So we're not going to go here. We're going to go all the way here. I'm just going to click on it. I'm just going to double click on it, and we get here, boom. We get a bunch of print statements. Speed. We're outing displays foreground process dash I. We're what else is there? Let's see. Usage. So yeah, and if you actually did watch the keylogger, keylogger video, this makes way more sense. So let's say SIL is 0. So there isn't less than 2 command line arguments. We did not input dash help or dash dash help. We go here and we get to this. And actually, I'm gonna revisit this in a later video because I really have not even done this myself. So yeah, I'm gonna do the introduction tutorials to reverse engineering, just basic stuff, then I'll revisit this. But yeah.